Hello there, this is lecture 22 in Emergent States of Matter, and today we're going to be talking about response correlations and broken symmetries in systems with continuous symmetries. So just to orient you, in the lecture notes, the printed lecture notes, we're going to start off today by talking about section 4.4, which is on correlation and response. And it applies to both discrete and continuous symmetries. We'll present it following the notes as if we were talking about discrete symmetries, but it doesn't make much difference. And then we will get into the meat of this chapter, sections 4.6 to 4.12, leading into Goldstone's theorem and other aspects of spontaneous symmetry breaking with continuous symmetries. So let's start this by writing down the Landau free energy, and I'm going to start off. So this is section 4.4. I'll call this correlation and response. And what my goal is in this section is to explain how to compute correlation functions. And what information they tell you. And in general, what we're going to see is that there's this sort of connection between correlation and response functions. And we're going to see that these are rather general connections. And the ultimate goal of these things is this connects spatial structure with thermodynamics. Now, all the calculations that we're going to do in this course are basically at the level of Gaussian approximations. So we're going to see simple ways to compute these things in what are called a Gaussian approximation to functional integrals. So that's what we're going to do, and these results are very general, and they apply to discrete and continuous symmetries. And then in the next section, in section 4.6, after we've done this, after all of this, next we're going to look at the specific new features that arise when you have continuous symmetries. Okay, so last time we wrote down the Landau theory for systems with continuous symmetry, but I'm going to just slightly backtrack from that. I'm going to follow the notation in the notes, and so what we're going to talk about is the correlation and response for Landau theory. So we'll but I don't need this at all. I've already got my heading. So what we're going to start off then is with the Landau free energy, which I'm going to write in this form. And what I'm going to do now, just to make sure that everybody follows along, I'm going to keep all the coefficients in as they should be. I'm not going to non-dimensionalize and so on. So I'm going to write the free energy in the following form. So that's my free energy, and so H is meant to be some external field. T is meant to be T minus Tc over Tc. A and B and gamma are coefficients that are greater than 0. So in principle, we can non-dimensionalize that, but I've chosen not to. So the next thing that we want to do is I want to do some practice with functional methods, because it's been a while since you had a chance to look at them. So let's first of all explain that if I were to compute the order parameter expectation value, excuse me, then I can write that in the following form. So expectation of eta of r, I claim that this is equal to the functional derivative of the free energy with respect to the external field, like so. And I'll show you this in a minute, why that's so. I want to just comment that, as you've heard me say before, space is just a label. So notice that when I compute this object, I'm computing it at a particular point in space R, and so R is on the left-hand side, and so R has to be on the right-hand side, and so we're differentiating it with respect to the external field at the point R, and so those two R's are the same. So let's just see where this comes from. So just to make sure that everybody is on the same page. So we define the partition function as Z is equal to the trace of e to the minus beta times the Landau free energy. And because the Landau free energy depends on the external magnetic field, which is over here. So after I've integrated out the eta degrees of freedom, the order parameter degrees of freedom, what that means is that the partition function itself is a function of the field H of R. So what that means is you tell me what H of R is, you give me some function defined over space, and then the partition function will be some quantity that depends upon that. It will be an explicit function. And we're going to define this thing to be the same as the free energy, and that free energy is then going to depend on H of R. So this defines the free energy from the Landau free energy. So this is the Helmholtz free energy. So you can think of this as being the Helmholtz or thermodynamic free energy. And then the thing that comes in here, this is the Landau or coarse-grained free energy. And as we talked about a long time ago, I'm not going to go through this. This trace means a functional integral. Over the fields eta of R. So that's what we have. So let me now go and demonstrate why the order parameter is minus df by dh. So if I want to compute the expectation value of eta, so that is by definition the trace. Oh, well, it came back. So that by definition is the trace of eta, e to the minus beta L, divided by the partition function. And now I can obtain this eta on the floor down here. When I say floor, I mean this. So how do I get that? Well, I obtain that eta by differentiating with respect to h, because over here, look on the left-hand side, you can see that h couples linearly to eta, and so if I differentiate the partition function with respect to h, I can write this as 1 over z, and then dz by dh of r. And then, of course, the way I've defined it over here, I've got a factor of beta, and so that's going to bring down a factor of beta, and so I need to divide by a factor of beta. So I get something like this. So differentiating dz by dh will give you, d by dh of e to the minus beta. Let me write this as L naught plus h of r eta of r, like so. And so what that's going to give you is minus beta times eta of r, and this is the r that's in here, times the exponential. And so because of that, because of that, I can simply write down the expectation eta is 1 over z dz by dh of r. So if this looks unfamiliar to you, it's absolutely critical that you do that one line of algebra to make sure that you completely understand it. And so what I've just shown you then is that the expectation of eta is equal to 1 over beta, and now 1 over z dz by dh is d by dh of r times the logarithm of the partition function. And the logarithm of the partition function, z over here, is equal to e to the minus beta f. And so this then is minus df by dh of r. So that's where that comes from, because f is equal to minus kbt times the logarithm of z. Okay, so that's very simple. So hopefully everybody understands that. So the next question that we want to ask is a response question. how does the expectation value of eta at the point R change by a perturbation to H at a different point in space, which I'll call R prime. So the answer to that question is, well, what do we have to do? We have to compute the change in the expectation value of eta at the point R with respect to a change in field at the point R prime. And so this is an object that's going to depend upon two labels, R and R prime, and we're going to call this object the isothermal susceptibility, R and R prime. Now, the isothermal susceptibility that you learned about in thermodynamics is just demagnetization by the external field, but now we've generalized this to an arbitrary order parameter, and we've generalized it to an order parameter that is a field in space. And so let's now go and compute what this object is. So, of course, eta itself, the expectation value, is df by dh. So what this is a second derivative because we've differentiated once to get eta, and now we have to differentiate again to get h of r prime. So this is, I can write this as minus d by dh of r prime acting on eta, that will acting on df by dh of r, like so. And so that is equal to the second derivative. So now go through and check this. So now we're going to do the same thing that we did over here, but now we're going to do it a second time. So the first thing that you're going to see is that the first term that we're going to get is when we differentiate twice, we're going to bring down a second factor of eta. So this is going to be, once we differentiate the first time, we're going to first of all get a factor of 1 over kBt. And then what we're going to get actually, let me just make sure that you fully understand what I'm going to do now. So let me I know from experience that some students find this they get lost at just this point here. So remember that eta. On the previous page, eta is 1 over z dz by dh of r times 1 over beta, right? And so now what we're doing is we're differentiating that with respect to h prime. And so I've got a d by dh of r prime acting on 1 over z. Let's put that 1 over beta over here, 1 over z dz by dh of r. Okay, so that's exactly what it is. Now look at what happens when I act with d by dh on this. There's two things inside. So the first thing that this can act on is the 1 over z that's in there, and then the second thing it can act on is the dz by dh over here. And so once I differentiate 1 over z with respect to h, I'm going to get minus 1 over z squared dz by dh. And when I act on the dz by dh of r, that one is going to give me 1 over z times d2 z by dh of r dh of r prime. So when I put those things all together, what I'm going to end up with then is the first term is going to give me I get a factor of 1 over kbt in front, and then I'm going to get this, and I want you to check this, e2 of r prime minus e2 of r times e2 of r prime. Okay, so let's just make sure we understand that this term over here is going to give us this one, and this one over here is going to give us this one. And the reason you get this is that I've got 1 over z squared dz by dh of r times dz by dh of r. That's already there. And so that corresponds to then e2 of r squared, which is what I've got over here, and then averaged e to r prime, and then the second term here just brings down a second order parameter, and so I get that. So make sure that you can fill in the steps for that, and then we're going to define this thing to be then, this is then beta times g of r and r prime, and g of r and r prime is the 2-point correlation function. And in particular, what we've just proved is that the response function chi t of r and r prime is just equal to beta times the correlation function. This is the response to an external field, and this is the order parameter correlation. Now notice that what I've said in here is I've made the point that this is the order parameter fluctuation correlation function, not the correlation function itself. And why do I say that? Well, I want you to check this again. If you write, I can write G as the following. And I can write it like this. So this is the correlation of eta minus the expectation value, and then eta minus the correlation of the expectation value at the different point. So this thing here is delta eta of r, which is eta of r minus its mean value. And then this thing over here is delta eta of r prime, which is the same thing, eta of r prime minus the expectation value of eta at r prime. And so these quantities here are, these are just the fluctuation about the mean value. Okay, so I want you to make sure, if this isn't immediately obvious to you, I want to ask that you check this. And so you should check this by multiplying it out. And you'll wonder, what is the expectation value of the expectation value of eta? Well, the expectation value of eta is 3, some number, right? So what is the average value? What is the expectation value of 3? Well, it's 3 itself. So you'll see that this term over here, this is exactly the equivalent of what we have over here. Okay, so so that's the connection between correlation and response. And if we have a translational invariant system, then chi of r and r prime is just a function of the separation. And of course, the same thing for G. And so that means that I can write in Fourier space that the Fourier transform, let's denote that with a tilde of k, is equal to beta times the Green's function in Fourier space, G of k, like so. And so that's for translation invariant systems. Now, how do I make the connection to the usual thermodynamic susceptibility? So that usual thermodynamic susceptibility is simply the long wavelength limit. So in other words, the thing that we call chi t, which you might think of as dm by dh at fixed t in usual thermodynamics, this thing is just then the limit as k goes to 0 of this wave number dependent susceptibility. And you can see that is just beta times the correlation function in k space evaluated at k is equal to 0. Now, the Fourier transform at k equals 0, remember that g of k is the integral dr of g of r e to the minus I k dot r. I don't remember if I had a minus sign or a plus sign in the way I defined it. And so when I set the k goes to 0 limit, then what I have is that g hat of 0 is just the integral in real space of the 2-point correlation function g of r, like so. And so what I've learned then is that the isothermal susceptibility, which you learned about in elementary thermodynamics, is just beta times the integral over space of the 2-point correlation function. And so this connects the spatial integral of correlations with the static susceptibility from thermodynamics. And this relation here is a very important relation because it connects thermodynamics and correlations in a very general way, and it's an exact result. And this exact result has a name. It's known as the static susceptibility sum rule. And it's called a sum rule because you have an integral over the over real space of the correlation function. So that's the basic physics between these things. So what that says then is that if I want to compute how a system responds to an external perturbation, what I need to compute is the 2-point correlation function. And so now I want to show you next how we go about doing that. So the next thing that we're going to do how to compute the 2-point correlation function. And we're only going to compute it in Gaussian approximation. So we're not going to be doing it in full gory details. So you'll see where we make those approximations when we get there. So what is the basic idea? So the basic idea is to literally differentiate the Landau free energy in order to get the order parameter. And then from that we can do a further differentiation in order to get the actual correlation function. So let me write it down in this sort of more organized way. So step 1 is we're going to compute the mean value eta of r by differentiating the Landau free energy and requiring that it be stationary. So that's step 1. And then step 2 is a second further derivative with respect to a field h of r to get the equation for chi t of r and r prime, i.e. the Green's function, the correlation function, g of r and r prime, from the sum rule, from the static susceptibility sum rule. Okay, so that's the basic idea, and why this works. I'm not sure if I'll take the time to explain this in full detail, but let's see how far we get. Okay, so step 1. So the idea is that we want to compute the expectation value, and so we're going to require that the L ID eta of r is equal to 0, and L is the Landau free energy that we started with wherever it was, so down here. So that's going to that determines the mean value, and so let's just differentiate it. So you should know how to differentiate functionally all of the terms in this function, in this functional. You did that in the first homework. So if necessary, revise that. So I'm just going to go and simply write down what you get. So when you take the first term, when you differentiate that, that's going to give you a term minus gamma del squared eta of r. And then the derivative of the second term is going to be 2at eta of r, like so. And then the derivative of the third term is going to be 2b eta of r cubed. And then h of r, eta of r, when I differentiate with respect to eta, that's just going to give me the factor h of r. And that, this is the thing that is dl by deta, and so this thing has to be 0. So that's the idea. That's what defines the mean value. Okay, so what we found is that the mean value eta satisfies this differential equation, and let me just note in parentheses that this equation is similar to the Ginzburg-Landau equation. In superconductivity. Okay, so that's the first equation. Then step 2 is what we're going to do is differentiate with respect to h of r prime dl by d eta of r. And because dl by d eta of r is equal to 0, then this thing is also equal to 0. So now what we're going to do is differentiate every term in the above equation with respect to the field h. Now, when we differentiate eta with respect to h, what do we get? Well, d eta by dh is just what we mean by chi. Okay, so here we are. This is when you differentiate eta with respect to h, that gives you chi. When you differentiate h with respect to h, well, you have to now look at what the label is. Here you have h of r, and we're differentiating with respect to h of r prime. So dh by dh of r prime is just equal to a delta function. So now we can write down what we're going to get. So what we will get then is minus gamma, and then del squared. We're differentiating with respect to h of r prime. H is a different field. R prime is just a label. So that goes under the del squared, and then d eta of r by dh of r prime is just chi of r prime. So that is just going to be the following. D eta by dr, d eta by dh is just going to be chi, and eta cubed by dh is going to be 6 eta squared times the eta by dh by the chain rule. So let's write this down as minus gamma del squared plus 2at plus 6b eta squared times chi of r minus r prime, and then that equals dh of r by dh of r prime, and that is equal to delta of r minus r prime. So make sure you can do that. And then remember, we have the static susceptibility sum rule. That's this relationship that we have over here. And so I can then write this as beta times minus gamma del squared plus 2at plus 6b eta squared g of r minus r prime is equal to delta of r minus r prime. And so you can see that there's another terminology that you've surely heard, which is that the correlation function is a Green's function. Because it satisfies some operator acting on it is equal to a delta function. And so it's the Green's function of the operator on the left-hand side. And so response, correlations, and Green's functions, they're all the same thing. Okay, so this is the result. This is a differential equation. So so how do we use this? So now let's see what it really means. So let's now look at this equation. Above and below TC. So when T, which is just to remind you, is T minus TC over TC, is greater than 0, then that means that the expectation value of eta should be 0, and when it's less than 0, then we know that the expectation value of eta is equal to well, let's just say it's non-zero. Okay, so and in the assuming that there are no spatial variations, these will be spatially uniform. So eta is equal to minus AT over B. So this is something like minus AT over B square root. Okay, so that means then if I look at this equation, I can rewrite it in the following form. So we can rewrite in the following form. I can write this operator, the one we have on the left-hand panel, as minus del squared plus a term which I'm going to call psi to the minus 2 d of r minus r prime is equal to kbt over gamma times delta of r minus r prime. So let's just see what I did there. So what I did was I put in the values for eta. So when eta is equal to 0, then this term that I'm writing down here on the left-hand side is going to vanish. And so the equation has the form of minus del squared plus a constant. And I've written that constant as psi to the minus 2, because this has dimensions of length squared, of inverse length squared. And so therefore, this psi has dimensions of length. And we'll see that it has an obvious interpretation. And we can read off what it is. So this xi is just gamma over 2at to the 1/2 when t is greater than 0, just from looking at what happens over here. So you can see there's the gamma over 2at. I've divided by gamma on the right-hand side, so that's where that goes into. So that's true. And then when t is less than 0, this has the form minus gamma over 4at. Again, to the 1/2, and there's a minus sign because t is less than 0. So this correlation length, which is what this thing is going to turn out to be, this correlation length has a different multiplier above and below TC, but has the same functional dependence. So we can see that this length scale psi goes as t to the minus nu, where nu is equal to the 1/2, and so this tells you that the correlation length diverges with the square root singularity as we go towards the critical point. In other words, as t tends to 0 from below or from above. Okay, so that's great. So we've seen that the correlation length diverges, and we've seen that it diverges with a critical exponent nu. So now let's solve. The next thing we want to do is solve for the functional form of the two-point correlation function. Now we can do that because the equation that we're dealing with up here has a name. This equation is known as Helmholtz's equation. And you first encountered it most likely in electromagnetism, and you also encountered it if you did elementary particle physics. It's the equation for the usual propagator of a massive particle in the free field approximation, and so that's also known as the Yukawa equation. So we can solve it in two different ways. We can solve it by two methods. We can do it by Fourier transform. Or we can use our knowledge of special functions. And in fact, this equation is a form of Bessel's equation. So let's go ahead and do that. So let's do the Fourier transform method first, because that's the most easy. So I've got the equation minus del squared plus xi to the minus 2, g is equal to some delta function on the right-hand side. So if I take the Fourier transform, then the Fourier variable g hat of k obeys the equation k bt over gamma 1 over k squared plus xi to the minus 2. And if we look at t equals tc, then xi is equal to infinity. And so we can see that g hat of k evaluated at the critical temperature is just equal to kBt over gamma times 1 over k squared. So the correlation function in Fourier space decays with a power law with an exponent minus 2. And if I write this in real space, this is equal to kBt over gamma and r to the power minus d minus 2, at least for d greater than 2. So what we've learned from this is that at the critical point, correlations decay slowly. In fact, specifically as a power law. And that's probably something that you already know. So this prediction that we've just found is from Landau theory is not quite correct. And it's not quite correct because we only dealt with interactions. Of eta, self-interactions at lowest order. If I get time, I'll show you that. So this is a mean field Landau theory result in the so-called Gaussian approximation. So what the approximation is that we've made, I'm not going to really go into detail right now, but I'll try to show you later. So actually the correct result, which is a normalization group result, is that G of R and Tc goes like R to the minus D minus 2 plus eta. This eta is not the order parameter. This is a critical exponent or anomalous dimension. And in 3D, it's pretty small. It's about 0.01. So, but anyway, that's the whole question of anomalous dimensions at phase transitions. That's a topic that we'll deal with ad infinitum in the renormalization group course. Okay, so that's true exactly at Tc. Now, what about T not equal to Tc? So then what we have is that G K is equal to KBT times the isothermal susceptibility, the static isothermal susceptibility from thermodynamics. So that's the long wavelength limit, and then over 1 plus k squared xi squared. So I've just divided top and bottom and written it like this. So this is the functional form. And so now what we have to do is do the inverse Fourier transform. So in this formula, you should note that the static susceptibility is just the correlation length squared over gamma, and so we can see that scales like 1 over T minus Tc over Tc as you approach the critical temperature. So what this tells you then is that near the onset of a phase transition, so near the onset of the emergence of an order parameter, the susceptibility diverges. So the system is very sensitive to perturbations. And this makes sense because what it means is that we're very close to the system spontaneously ordering. So the system is close to spontaneously ordering. And so needs smaller and smaller pushes to order as the temperature gets closer to Tc from above. So that's the interpretation of it. And another way that we can say this is that as T tends to Tc from above, the unordered phase becomes unstable. And this causes correlations to grow. Okay, so now what we could do is we could imagine that we take the formula that we have over here, and we could do the inverse Fourier transform of that, which you can certainly do. But let me show you a different way to do it. So what I want to do now is switch gears and calculate this from special function theory. So for t not equal to Tc, I'm going to, instead of just doing the inverse Fourier transform, which requires some complex variable technology, which I don't want to spend the time doing, we'll just do it in real space. So why do we do it in real space? Well, we notice that the delta function is spherically symmetric. And so that means that we expect that g of r is really just going to be a function of the magnitude of the vector r. It's going to be spherically symmetric. And so the idea is that we can decompose the Helmholtz equation in spherical polars. So that's exactly what we're going to do. So if I do that, then what I can do is I can write it in the following way, writing del squared into d-dimensional radial polar coordinates. So what I get is this minus 1 over rho to the power d minus 1, d by d rho of rho to the power d minus 1, d by d rho plus 1. So that operator acting on a function which I'm going to call capital G of rho is equal to little g delta of rho. And what is rho? So the variable rho is just r normalized by the temperature dependent correlation length. So it's a dimensionless variable. This capital curly G of rho is just the same thing as little g of r over psi, like so. And you can read off that the variable little g is just kbt over gamma times the correlation length as a function of t to the power 2 minus d. And you can probably imagine that strange things happen in 2 dimensions. So this equation is Bessel's equation. And so we simply look it up in Abramovitz and Stegun, for example. And what we find is that the following solution. So let me write it down. 1 over g G of rho has the following form. Now it depends on the dimension, so I'm going to write it down in steps. So it's going to be e to the minus rho when d is equal to 1. So you can solve that exactly. And when it's not equal to 1, it has this form. And with any luck, I'll write it down without any misprints. So it's equal to this thing in the in d greater than or equal to 2, and this thing here is called the modified spherical Bessel function of the third kind. It's sometimes called the McDonald function. And again, this is just something that people, worked out, Bessel's equation, Sturm level theory throughout the 19th century. Let me just write down the functional form. So K n of rho scales like this. It goes as pi over 2 rho to the 1/2 e to the minus rho when rho goes to infinity. So in other words, the McDonald function of the nth kind, all of them scale as exponentially as the argument goes to infinity. Now the argument is this rho, and this rho is r over psi. And so what that means is that the correlation functions decay at long distances exponentially over the scale of the correlation length psi. So that's the first thing as rho goes to infinity. And then when n is equal to some arbitrary number and rho goes to 0, the behavior looks like this. So it looks as the gamma function, always as gamma function of n over 2, rho over 2 to the minus n as rho goes to 0. So near the origin of the small values of the argument, it decays as a power law. And if n is equal to 0, so we're looking at k0 of rho, that's what's going to happen in 2 dimensions, then the behavior is actually logarithmic rather than power law. So what that means is that the behavior of the correlation functions looks something like this in general. So what we found is that for rho greater than psi, this thing decays exponentially. And then for rho less than psi, this thing is decaying as a power law. And then the two things cross over at around the correlation length. It's not meant to be quite as sharp as what I've drawn over here. But so the idea is as I go toward the critical point, this correlation length, this psi, goes to larger and larger values. As t tends to tc, And so it pushes the exponential behavior off to infinity. And then as it does that, the result of that is that then the exponential behavior is pushed off to infinity. And what you are left with only power law decay of correlations. So sometimes you'll hear people say that if I have a second order phase transition, it's a crossover between exponential decay and power law decay. But really what's happening is that the correlation function is taking the same form. It's just that the place where the functional forms cross over is going to higher and higher values of space. And let's see, what else do I need to explain in this? Oh yes, I didn't explain this. I also need to say that over here, when I wrote down gamma of n, that was Euler's gamma function. So that's the integral from 0 to infinity, t to the n minus 1, e to the minus t dt, and that is equal to n minus 1 factorial when n is an integer. Okay, so what that tells you is that the correlation lengths decay essentially exponentially at large distances. Okay, so I think that's this is all generally true, whether discrete or continuous symmetries, and so now what I want to do is I want to jump forward now and apply what we've learned to looking at the correlation functions now when we have a continuous symmetry. So now what we're going to do is we're going to look at the susceptibility when you have a continuous symmetry. And so this is going to be sort of, more of the same, but what's going to be different is that we will be we will take into account the spatial structure. Okay, so I think I'm going to go with that. So let me just make I want to make a comment in here. So before I get into that. So these results ignore fluctuations beyond second order. So we think of them as being just results of Landau theory. Now in the notes, I may come back to this later if people would like, but in the actual class notes, this is described. Let's see, where is it described in detail? Why all this works? So I'm going to skip over this for now. So I'm just going to say C 4.4.1 addendum for further details. And basically what I show there is why is it that we use mean field theory, which supposedly doesn't have any fluctuations, to calculate a theory which does have fluctuations, at least to lowest order. So how it is that by just differentiating the Landau free energy, which is a mean field free energy, we can get something to do about fluctuations. That's something that you may find surprising, and it is surprising and requires explanation. And so in the notes, in the printed notes, that's section 4.4.1, the addendum. And if people want, later on, I can go over how to do that, or maybe an office hour, and explain that for you. Okay, so now let's talk about the susceptibility tensor. Okay, so what is the basic idea here? So we're now going to go back to the ON model that we talked about last lecture. So we're going to consider the ON model and how it responds to an external field H, and that field H is along the direction n hat in spin space, in order parameter space. So I'm going to call spin space and order parameter space. I'm going to use in terms interchangeably. Spin is slightly shorter than order parameter, so I'll just call it spin space. So the idea is that when we apply the field, what's going to happen is that the spins will order along this direction n, and so I can write the magnetization, which is what we'll call the response, is I'm going to call that m alpha. So alpha goes from 1 to n, and that is the expectation value of our order parameter field S alpha as a function of space, and that is going to be some magnitude n along the direction n alpha. Okay, so let's take the direction in spin space to be the unit direction along the first dimension. So I'm going to write it like this. So now what I'm going to do is I'm going to define the 2-point correlation functions, but the 2-point correlation functions are going to be different for different directions. So I'm going to define two-point correlation functions, and it's going to be easier for me initially to define them in momentum space. So I'm going to write G parallel of K, and that's going to be defined as the expectation value, the absolute value of S in the one direction as a function of K squared, like so. Okay, so that's going to be called G parallel. It's called G parallel because it's the response in the direction in which you're applying the external field. And then I'm going to define a G perpendicular of K. And I'm going to define it in the following way. I'm going to put in a factor of V, delta of K plus K prime 0, and then delta alpha beta. So that's going to define for me a scalar quantity G perpendicular K, and this is going to be S in the alpha direction as a function of K, S in the beta direction as a function of K prime, and then the expectation value, what happened? like so. Now the one direction is the direction of ordering. So in this case, alpha and beta have to both be not 1. So they have to be greater than or equal to 2. And so this this one here is parallel to the H, and this one here is perpendicular to the H field. And of course, there's all these directions, n-1 directions perpendicular to H. So in what we're going to be doing now, we're going to define this will always mean longitudinal, which means parallel to the direction of ordering, parallel to H, and this is going to always mean transverse, which means orthogonal. To the direction of ordering. Okay, so these are two correlation functions. And because I've got two correlation functions, I have two static susceptibilities. So the corresponding static susceptibilities are chi perpendicular is equal to g hat perpendicular k equals 0, and chi perpendicular is equal to g perpendicular at k equals 0. Okay, so that's just from the static susceptibility sum rule. So where do these things come from? So these things come from the susceptibility tensor. So let's now introduce the susceptibility tensor. So what we had before was we had a chi that we differentiated with respect to the external field. So we had a chi, which was a sort of dm by dh. That was the thermodynamic one. So this thing is now going to go to a tensor, which I'm going to call chi alpha beta. So this is the case for a scalar. This is just the usual thermodynamic susceptibility. And now this is going to be generalized to a susceptibility tensor. Okay, so this is not to do with the fluctuations. This is just the regular thermodynamics. So let's go ahead and do that. So I'm going to define chi alpha beta to be minus d2f by dh alpha dh beta. Now these h's are constant fields. These aren't functional derivatives. These are partial derivatives. So we're just talking about the thermodynamic free energy here. So we've defined it like this, and this is the same thing as dm alpha by dh of beta. So this is just the obvious generalization. It tells you the response of the magnetization in the alpha direction to a change in the field in the beta direction. And my F here, F is equal to the free energy per unit volume. And that free energy per unit volume is basically just going to end up coming from the uniform part of the free energy, the thing that we called the potential before. Okay, so this is the in the spatially uniform case. I'm just taking out the factor of the volume and writing the total F is F, little f times V. Okay, so this chi alpha beta, what it tells you is how the alphath component of the order parameter varies due to a change in the betath component of the external field. And we don't really care about the actual, what the field is. What we're interested in is the limit as the magnitude of the external field goes to 0. Just as when we look at spontaneous symmetry breaking, we want to look at what happens when the field goes to 0, because that's where the phase transition occurs. So we're interested in the limit as h tends to 0, because that's when the phase transition occurs. To the emergent state, and that emergent state is one that has degenerate minima. As we saw from the picture of what the free energy looks like. Okay, so that's what we're interested in computing. So now let's think about what symmetry tells us about this. So what symmetry tells us is that the Hamiltonian has ON symmetry. Okay, it's rotationally symmetric in spin space. I make a change in, change the order parameter. It doesn't change the free energy. And so what that means is that F, the free energy per unit volume, cannot depend on the direction of H. So what that means is that F, which you might have thought is a function of the vector H, is actually a function of the scalar H. And by scalar H, what I mean is the absolute value of H, which is H, the norm of this vector, which is the sum of the squares of the components of H, square rooted. Okay, so that's so the free energy must depend on that, and we're going to utilize this fact because when we compute the derivatives to compute the susceptibility, we know that everything must finally depend on just the magnitude of H. So so now watch for the algebra. Everything can only depend on H. When I write H without a vector, I mean just the magnitude of H. So let's see what that means. So when I have to compute my derivatives, I have a term which is dH by d alpha. Well, dH by d alpha is the same thing as d by d little h times d little h by dH alpha. And I know what H is because it's defined like this. And so I can compute what this is. And dH by dH alpha is just H alpha over H itself times d by dH. Okay. So then when I compute chi alpha beta, that's going to be the following. It's minus d by dh alpha of df by dh beta, and df by dh beta is h beta over h df by dh. And so now there's two terms. Well, actually, there's three terms. The d by d alpha on the outside acts on the beta, the h, and the d2f by dh squared. So let's just go through and differentiate each term. So dh alpha times acting on h beta is, of course, just a Kronecker delta. So I get minus delta alpha beta 1 over h df by dh. Then I get a term h alpha, h beta over h times minus 1 over h squared df by dh. And then lastly, I get a term minus h alpha, h beta over h squared d2f by dh squared. And these things come from the following terms. So this one comes from this acting on here. Then this one, so that's this term, and then this second term is this thing acting on here. So that gives me this term over here, and then lastly, this thing acting on here just gives me this last term over here. So it's quite easy to see where all these things come from, and I can put it all together, and so that gives me minus h alpha, h beta over h squared d2f by dh squared minus 1 over h df by dh times delta alpha beta minus h alpha h beta over h squared. Okay, so you're probably realizing what these terms represent. This term on the right-hand side, some of you will recognize that as a transverse projection operator, and indeed that's what it is. It's going to end up being the transverse part, and the other part is the longitudinal one. So remember that h, the vector h, is equal to its magnitude times the direction of ordering. And so what that means is that when I write things down like h alpha, h beta over h squared, that is just the normal, that's just the vector n alpha n beta, where n is this unit vector. And so I can write that chi alpha beta is equal to n alpha n beta chi parallel of h plus delta alpha beta minus n alpha n beta times chi perpendicular of h. So those are that's splitting it up into longitudinal and transverse parts. And we can read off then that chi, the longitudinal susceptibility, is just chi parallel of h is equal to minus d2f by dh squared, and the transverse susceptibility is just given by chi perpendicular of h is minus 1 over h df by dh. And Remember df by dh is just m, so this is m over h. So what does it mean? We're going to see exactly what this means, what the consequences of this are. But if the external field h is in the same direction as m, then you just get the susceptibility chi-parallel. If h is in the orthogonal direction, you get the susceptibility chi-perpendicular. So that's what these things mean. Okay, so I think that's the algebra. It's not very difficult. But now let's look at the rather remarkable consequences of it. So this is section 8 in my notes. This is the excitation spectrum for t less than tc. And what I'm going to show you is, at least at this level of approximation, what's known as Goldstone's theorem. Okay, so what we're going to see then is that there's a special structure in the ordered phase when there are continuous symmetries. So let's look at t less than tc, and so what's going to happen is when h is equal to 0, the system is going to order. So you're going to get long range order. And m is going to be non-zero. So there's some non-zero expectation value of the spins along some particular direction. So h is equal to 0 and m is non-zero. So what that means is that you can see over here that chi-perpendicular what you're going to see is that chi-perpendicular then is going to diverge as h goes to 0. And so I can write then that chi-perpendicular, when h is equal to 0, is equal to infinity, or perhaps more reasonably, I'll write that the inverse of chi is equal to 0. And so that means that the transverse correlation function is equal to 0. So what that says is that the susceptibility in the transverse direction is infinite. So susceptibility to perturbations in the transverse direction is infinite. And what that means is you only need an infinitesimal field to rotate the direction of ordering by a finite non-zero amount. So where does that come from? You might think, wow, some weird divergence or something strange like that, but it's pretty obvious where it comes from. So let's flip back a couple of blackboards. There we go. So let's grab this one, see if we can pick this up. There we go. Let's copy that. Okay. And then let's go over here. Paste it into here. So let's stick it over here. And then let's go back to where we were. Okay, so let's go back to where we were. Here we are. And let me just clean this picture up now. We've got this thing here. I don't care about that. So where does this come from? Well, you can see that there's this degenerate global minimum along here. So let's suppose that the system is ordering along that direction. I'm going to make this big just so that you can see it. So let's suppose that the direction of ordering is here. Then in order to rotate the direction of ordering to somewhere over here, let's say, it costs no energy to do that. And so that's why it is infinitely susceptible, because I only need a very small infinitesimal change of force to move it an arbitrary amount. So this degeneracy excuse me. So this degeneracy is the reason for the infinite transverse susceptibility below TC. Okay, so you could say, great. Well, what about the longitudinal susceptibility? So let's go and look at the longitudinal susceptibility. And let me, how about we try this color, and let's make it big so you can see it. Okay, so now let's ask what happens if I make a longitudinal variation. So a longitudinal one would be like this. I have my vector like this, and now I want to make it longer in the same direction, or shorter, if you like. So you can see that in that direction, the potential, if I go either go longer or shorter, then I will get, I will raise the energy of the system. So if I, on the other hand, a longitudinal variation in M costs energy. And so it's not infinitely susceptible. So now we're seeing something very different between the longitudinal and the transverse fluctuations. They all have a different character and a different effect on the response function. So let's just summarize that. So in other words, let's just say it like this: when the ON symmetry of the Hamiltonian is spontaneously broken. There are two classes or two sorts of fluctuations. Those that are parallel to the ordering direction, and those that are perpendicular. So the longitudinal ones experience an energy penalty when you increase or decrease m, which is the magnitude of the order parameter. On the other hand, orthogonal or perpendicular fluctuations change the direction of m, not its magnitude. And cost no energy. Okay, now all of this was true for a spatially uniform system. Okay, so now let's ask ourselves, what happens then when spatial variations come into the picture? So the next question is, how do spatial variations affect this picture? Okay, so now we need to consider the gradient term. In our Hamiltonian, and we defined a Hamiltonian with a minus sign. So what we expect then is by continuity, the longitudinal fluctuations will still have a finite energy cost. And that finite energy cost will get greater as I increase k, which means I make faster and faster spatial variations. On the other hand, the transverse fluctuations will now have an energy cost and that energy cost is going to be proportional to grad s squared. So what that means is that the longer the wavelength, the smaller the energy cost. So what that means then is that if I look at the excitation spectrum of the system, must have low-lying modes. Whose energy, which I'm going to call epsilon of k, has to go to 0 as k goes to 0. Okay, so what we're saying is this: if I have a system that if I have my spins and if I rotate them uniformly, it costs no energy. Now suppose I rotate them non-uniformly, so I keep my spins over here. These are my two fingers. There's the spins, and now what I do is I rotate this spin, my left finger, my right finger, whatever it looks like to you. Then, depending on how far apart my left and right fingers are, the gradient energy is going to go like grad s squared, which will go like k squared. And so as that wavelength gets further and further apart, the energy cost for those spatial variations gets smaller and smaller. And so we know that those modes have to go to 0 as k goes to 0. So then you may say, okay, well, you said that there have to be these low-lying modes. Well, how many of them do there have to be? And that's easy to answer because it's going to be for every transverse mode. All the longitudinal modes always have an energy cost, and so therefore they will have a gap in their spectrum. They will have a gap. They will have a finite energy plus some part that depends on k squared. But the transverse modes are the ones whose energy goes to 0 as k goes to 0. And so the answer is going to be 1 for every transverse mode. In other words, in the ON model, that's equal to n-1. So that means that when we write down the energy spectrum, it's going to look something like this. So here's K. Here are the low-lying modes. And then what we've just determined is that there's going to be a bunch of modes that are low-lying. So these are the low-lying modes. And there's going to be n-1 low-lying modes. And then there's going to be another mode, which is not low-lying at all. So this is the longitudinal we say gapped mode. Because there's a gap. And that gap reflects the curvature of the potential that we see over here. So those modes are gapped, and then there's n-1 modes that are low-lying. And so these modes are known as Goldstone modes. And after Jeffrey Goldstone, who sort of proved this in more generality, quantum mechanically. Okay, so one of the things I want to make sure you understand is that there's a very important aspect of these modes that is frequently misunderstood, and that is that not every low-lying mode, meaning a mode that goes to 0 as k goes to 0, Not every low-lying mode is a Goldstone mode. Okay, we only use this term for modes that arise as a consequence of spontaneous breaking of a continuous symmetry. And spontaneous symmetry breaking of continuous symmetry. Are Goldstone modes. So I'll let you think about what other modes there could be that are low-lying that are not Goldstone modes, and we'll talk about that next time. All right, so next time we're going to look at what are the consequences of these Goldstone modes for the functional form of the correlation functions below TC. Okay, that's it for today. Thanks a lot.